Hello everybody, my name's Phil. I've been a college chemistry teacher for over 40 years. I'm become very interested in climate change, and I recently read the 42-page summary of the IPCC6 full report. The full report is very intimidating, which I haven't read. It's almost 4,000 pages, has a couple hundred plus authors in the vicinity of 14,000 literature citations. So I just read the 42-page summary, and I thought I'll make an abbreviated version of that in case you don't want to actually read the whole 42-page summary. I do have the link for that here if you want to take a look yourself. I thought I'd start off with a quote from Jacob Bronowski. "Dream or nightmare, we have to live our experience as it is, and we have to live it awake. We live in a world which is penetrated through and through by science, and which is both whole and real. We cannot turn it into a game simply by taking sides." So we basically have to confront the reality of climate change, and that's my goal in trying to summarize this data. It starts off with about 3 pages of narrative, and I think it's mostly data. I don't think there's a lot of the scary consequences that people are always posting. The report uses a 50-year period, 1850 to 1900, as a reference period or a baseline for looking at temperature and carbon dioxide and a few other things for comparison with current values that we're living with today and future projections. I just picked a few of the points and summarized them here. The top 3 greenhouse gases in 2019 were carbon dioxide, methane, and nitrous oxide. The last 4 decades are the warmest in recent records, and each decade has gotten progressively warmer. Global precipitation has been increasing since 1950 and increased even faster since 1980. In fact, this past year had some torrential rains in China and Germany. Storm tracks have shifted poleward in both hemispheres, so those would be typhoons and hurricanes. Human influence is causing a retreat of the world glaciers, snow cover, and alarmingly the Arctic sea ice. Upper oceans have been warming to 700 meters deep since the 1970s. Oceans are about 30% more acidic than in the previous millions of years. Sea level has risen about 0.2 meters, that's about 8 inches, since 1901 in the last century, and the rate is increasing. So 8 inches doesn't sound like much, but it's going up fast. Climate zones in both hemispheres are shifting poleward, so towards the North Pole, towards the South Pole. Growing seasons have gotten 2 days longer per decade since 1950s. That gives us about 14 extra days. All the figures I use in my slides come from the 42-page summary of the IPCC6 report. The first one I want to look at is the global surface temperature relative to 1850 to 1900. All right, so if we start back here, here's 1850, and if you look at the plot here, there's 3 colors of lines. There's the black line, which is the actual observed temperature. There's the brown line, which is the simulated human and natural causes effects. And then there's sort of the blue line here, which is just simulated natural causes only. So if we follow them out, you can see, around 1950, 1960, things start going up. They were going up a tiny bit here, but not noticeable. It's only in recent decades that we've had major jumps. So we start here, and we're going to go up to this level right here, which is actually probably about 1.1 degrees Celsius increase. And the simulated version looks pretty close to that. If we take out the human influence, you see it's pretty flat as we go across, so there's no major increase. There's some interesting spots along the way. If you look right here, this is about 1912. They had the biggest volcanic eruption in the 20th century here, and that puts out sulfur dioxides that kind of block sunlight coming in and actually cools the earth, so you can see there's a cooling there. The second biggest was Mount Pinatubo in the Philippines, and you can see that that had an effect probably too. This is kind of interesting. This period right here is when World War II was going on, and you can see there's a pretty big jump here, and then it falls back down. Probably a lot of energy put out during World War II. What I did was I went and looked at geological warming, like say coming out of the last ice age, and the world temperature went up about 8 degrees over 20,000 years. Very slow increase. That was about 0.0004 degrees per year. What we've been doing right here is we've gone up about 1 degree in maybe 50 years. So that's 0.02 degree per year. And so I divided those out just to show how fast we are increasing the temperature. And it comes out about 50 times faster than the geological increase in temperature out of the last ice age. So we're really going fast. This is the 1.1 degrees Celsius increase I just mentioned, and this is a repeated of over here. But what this does is breaks it down a little bit, so it looks at only the greenhouse gases. So this is kind of shocking because the greenhouse gases should be heating our world at about 1.5 degrees. The reason they're not is because when we burn coal, we also put out sulfur dioxide. And the sulfur dioxide blocks the sunlight and actually keeps us cool. These are aerosols. And so that cools the earth down. So you might say, well, we should do this. We should put this out. But in fact, this makes acid rain when it rains out of the atmosphere. So that's one negative. But also, it comes from burning coal. Coal is very dirty and has spread mercury all over the earth because there's also mercury in coal and all sorts of other things. So this isn't something we really want to do. Now it's broken down a little more over here. So they took this 1.5 degree increase and they looked at it from the point of the different fossil fuels, or the different greenhouse gases. And you can see that from the carbon dioxide, that's definitely the biggest component there, 0.8 degrees. But notice how much methane is. Methane is also a very strong greenhouse gas, even though there's a lot less of it. It's 80 times stronger as a greenhouse gas than carbon dioxide. Now it gets oxidized pretty quick, about 20 years it's gone, but we keep putting more and more out. So this is a significant part of our problem, is the methane. Nitrous oxide is down here, so if that's all we had to worry about, it wouldn't be a problem. But that's coming from fertilizers and natural sources. Here's that sulfur dioxide that's going against the increase. It's actually cooling our earth. So I won't go through all the rest of them. Now in the report, the IPCC6 report, they put forth 5 scenarios. Okay, so we'll start down here. Now they're saying 2015, and I'm going to use 40 gigatons per year, gigatons of carbon dioxide. And this could be gigaton equivalents too. So if I come up here and look at giga is a billion. It's a big number. That's 10 to the 9th. And when they say tons, they're talking metric tons, so that's 2,200 pounds. So that's where we're starting right here, when in fact, I think 2019, this was actually 43 gigatons. Now, if you look at the first 2 scenarios, these look fantastic. Okay, this is what we wish we could do. So you follow the first one down here, and they have a complicated name for these scenarios. I'm just going to say scenario 1. There's 2 ones. So I'll say scenario 1A, scenario 1B, scenario 2, scenario 3. There is no scenario 4. Scenario 5. Okay, so let's look at scenario 1. What that's telling us is we're going to start cutting our carbon dioxide emissions down from the 40, and we're going to start dropping it by 2060. We're going to go to 0. Doesn't sound very realistic, and it's not. Okay, if we could do that though, okay, you can see we just keep going down, down, down. We actually go negative from that point on. The second scenario also isn't very realistic, but it also says we're getting control of things right away. We're going to lower the carbon dioxide emissions, and maybe 2080 we'll go below 0 and lower it down. So these two, this is our dream world. This is what we wanted to do, but probably not going to happen. Okay, the third scenario would be we really get moving. We decide this is real. We're going to do something about it. So we keep going up for a little bit because it's hard to quit burning those fossil fuels. But then we get control, say by 2050, 2060, and we start to come back down. And by the time we get to 2100, we're only putting out 10 gigatons of carbon dioxide per year. So we're not 0, we're not negative, but it looks like things are somewhat under control. Now I call this line right here, scenario 3, business as usual. So we've been going up and up and up for all these decades, and if we just keep going up and up and up, what's going to happen is we're going to be putting out over 80 gigatons of carbon dioxide per year. Okay, that would be pretty much of a disaster. Now you might say, well, why would we keep going up like this? Well, there's going to be billions of more people on Earth. They want a better standard of living, and that requires energy, and that so far that energy comes from fossil fuels. So this is a possible outcome that we're looking at, not one that we want to see. This one right here is like major disaster. It says by 2090 we're going to be putting out 130 gigatons of carbon dioxide. So I call this one alarmist because it's not anything we want to see, but it's something that would be very dangerous. Not likely, the way we're doing things. The only thing that could possibly kick us up towards this level would be the permafrost melts, the tundra melts, starts releasing methane and carbon dioxide. Right now they're not thinking that's a likely possibility, but it is something to be concerned about. Now, there's a little number after each of these scenario 1, scenario 1b, and so forth. This is watts per square meter. So this is something, if you're not familiar with science, you might just not worry about this one, but this is a very concerning number. Now, watt is a very tiny amount of energy per second. So a joule is even less than a tiny calorie. And so that's just a very small amount of energy. And this says that at this scenario right here, we're putting out 2 watts per square meter. This one says about 3 watts per square meter. This one says a little over 4 watts per square meter, and so forth. They call this radiative forcing. And this is the thing that's heating up the world, is the amount of energy we're putting out per square meter. So it sounds small, but what we have to do is we have to consider the whole Earth, and we have to consider a whole year. So the whole Earth turns out to be pretty big. It has about 5 times 10 to the 14th of those little square meters, so we have to multiply that times that 1. And then for a whole year, it turns out we have 32 million seconds, so we have to multiply all those times this number. And that comes out after a year for the whole Earth, we have 2 times 10 to the 22 joules. Remember, joules is energy. That's an incredible number. We don't even know what that means, but it's a lot of energy from every watt that we're talking about. Okay, there's 2 of them here, so we'd have to multiply that by 2. Now, if we look at all the energy from all the fossil fuels we burn on Earth in 1 year, you know that's a massive amount of energy. That's 5 times 10 to the 20th joules. It's actually a smaller number than this number here. If we divide them out, then that means the energy from that 1 watt per square meter is 40 times more than the energy of all the fossil fuels we burn in a year. Okay, so every watt that we have up here, we have to multiply times 40. So if we come up here, business as usual, and look at this, okay, we're talking 7 watts per square meter. We multiply by 40, we'd be putting out 280 times the energy that we burn from all the fossil fuels on Earth in 1 year. And you can see why this is a big problem. Now, they have several charts. I just picked one of them here. The chart I picked is for temperature, because temperature is probably the most alarming feature that we're talking about. And it's also in red, which makes it a little scary. But they also have charts for extreme precipitation, for agricultural drought, for ecological drought, for soil moisture. So they have all of these predicted out for each of the temperature increases. They also have an intensity and frequency chart for 10-year and 50-year extreme events. We'll talk about one of those on the next page. So the first one is what has actually happened so far. Okay, we've gone up 1 degree. So the starting map is not going to have any extra heat. That would be just white. And then you can see that there's some red in here. So that red is indicated down here in terms of the temperature increase that we're talking about at different parts of the world. If you look up at the North Pole, it's a little more red than the rest of this, and that's because the North Pole is heating up about 2 to 3 times faster. So that's going on right now. This is the simulated version of that 1 degree increase. You can see they're pretty close, okay, not perfect, but it is a little darker red up at the poles, just like we have over here in reality. Now, if we come down here and look at the projected possibilities relative to 1850 to 1900, that's a 50-year period, and we go up to 1.5 degrees Celsius, notice that's a 50% increase in temperature. And from my way of looking, it's also a 50% increase in the problems that we're facing. So this is not a good result, but it's the result that we hoped for in the 2015 Paris Accords. So this is what the whole world was hoping for. Some people still are hoping for it, but we'll take a look. But if you look up here at the North Pole, it's a little redder than it was over here. And if you look at the rest of the world, it's a little redder too. So you can see how the heat is spreading around the world. Now, if we go up 2 degrees, this is quite a significant increase. Now we're talking about double the types of problems that we're seeing excuse me, types of problems we're seeing in the Earth today. And so it's a lot redder up at the poles. It's a lot redder on the surface of the Earth. This is something we don't want to see, but is very likely considering the way we're going. They even have a 4-degree increase projection, and all I can say is this looks really scary. Okay, it's so dark up here, and this is something we don't want to even contemplate. So this is why we have to act now. These little charts right here, a little bit different. What these do, what we're looking at here in this particular example is projected temperature increases from the global warming at 1 degree, 1.5, 2, and 4 degree relative to the 1850 to 1900 reference point, baseline. If we look down there, the dark dots depict frequencies and increases in intensity. And one chart is for 10-year extreme events, and one chart is for 50-year extreme events, relative to the base period of 1850 to 1900, okay, under the different warming scenarios. There's some other charts in the IPCC6 report that look at drought events and precipitation events and so forth, but I'm not talking about those here. So if we just look at this first column, this is the 1850 to 1900 comparison. And so what they do is they pick out the most extreme event in this 10-year period. All right, and that 10-year period is what they use to compare these other examples. So if we go up 1 degree, we're going to get 3 events that are equal to that most intense event back here. If we go up 1.5, we're going to get 4 of those events. If we go up to 2.0, we're going to get about 6 of those. And if we go up to 4.0, we're going to get like 9 of those, over 9 of those in a 10-year period. Now, remember, they're looking at 50 years here. So if we took 5 of those 10-year periods, we'd have to multiply this by 5. So that would be 15 extreme events because we increased the Earth's temperature by 1 degree. If we go up 1.5, which was the hoped-for goal, 5 times that would be 20 extreme events. And if we look at the 2.0 degree increase, which is what it's looking like, we multiply 5 times. So that would be 30 extreme events in that 50-year period where we're currently living. This one over here is we go and look at all 50 years and we pick the worst one. Okay, so that is the 50-year extreme event. If we go up 1 degree in temperature in our 50 years that we're talking about right now, we would have 5 of those events. If we go up 1.5, we're going to have about 9 of those events in the 50-year period. If we go up to 2, which is the most we want to see, we would have about 14 of those 50-year events back in 1850 to 1900. So you can see why this is a very alarming situation. And again, we don't want to even consider 39 extreme events. Sounds disastrous. So what I'm looking at here in this little chart is global ocean surface pH. So pH, that's something that not too many people know unless you took chemistry. But pH is a measure of acidity. But you've got to do your thinking backwards. So a lower number is actually more acidic in pH. Right? That's the way we want to look at it. So remember the SP1A, that had about 2 for the watts per square meter. This was the best we could hope for. And you can see we've come down a little bit in acidity. We've actually increased acidity a little bit, come down a little bit in pH, and so forth as we go down here. So what I did over here was I said, whatever the 1850 to 1900 pH was, that's the 0 reference point. And then if we hit the scenario 1A, we would make it 26% more acidic. And scenario 1B would be 35% more acidic. Currently, we're about 30% more acidic. And if we go to the scenario 2, we would be about 51% more acidic than we are now. And so this is the scenario I think that we're heading towards. And so I'll just look at this one. And so I just have a little comment here. Remember, the ocean is where all the plants and animals live, the sea life lives. And so what we're doing is we're taking their world that they live in, it's like our air, and we're making it more acidic. Say by scenario 2, be 50% more acidic. So just a little question, what would happen if we injected into your blood and made your blood 50% more acidic? You can see that would be an extremely dangerous thing to do. And so that's what we're doing to our oceans. We're making them more acidic, and we want to try and stop that. That comes from carbon dioxide dissolving in the water, making carbonic acid, which makes the water more acidic. If we look at global mean sea level, which is, people talk about this all the time, sea level rise from the melting ice around the world, that's another problem that we're facing relative to 1900. So we're starting out here, not too much, but if we keep increasing the temperature, which we're doing, more ice melts, the water level goes up. So this is the best case scenario. By 2100, sea level would go up about 1.5 feet. Doesn't sound like much, but you're talking about all of the coastal cities and ports around the world. You're talking about things like the Mekong Delta, which grows rice for a lot of Asia. So this is a very concerning thing that we're talking about here. And if we went to say this one right here, we'd go up about 2 or 3 feet. Okay, now they do have this little dashed line right here, and this is like a disaster. This is like worst case scenario, which would involve some sort of tipping point, like releasing methane and carbon dioxide from the tundra, which they don't predict that's going to happen in the next century. Could happen in the following century, but we're just trying to get through to 2100 right now. So anyway, this sea level rise is a problem. Okay, this is the last data slide that I have. This looks at estimates of carbon dioxide emission, historical estimates, and remaining carbon budgets. So if we start off here, this is what we've already done. From 1850 to about 2020, we've increased the temperature about 1.1. That came about because we've added carbon dioxide from 1850 to 2100, about 2,400 gigatons. Remember, giga is a billion tons. So that's what we've already done. Now, what we wanted to do is we wanted to stay under 1.5. Well, we've already done 1.1, so that gives us about 0.43 to play with, 0.43 degrees to play with. So what they did over here was they put in some probabilities if we keep doing what we're doing, or what's the maximum amount that we could do and meet this goal. So if we want to have 83% chance of probability of keeping under this, we can only add 300 more gigatons. But remember, we're adding about 40, actually a little more, and if we kept adding 40, it would take us 8 years to pass this up. Okay, well, there goes our 83% chance of staying under 1.5. Well, we could go and add 400, that would only be 10 years, and our odds would drop to 67%. Okay, if we go all the way to the worst one, that would be, we could add 900 more, and we only have 17% chance of meeting our goal, but we could add 900. That would be in 22 years, we would pass up that very low chance right there. Okay, that would be in 2043, which is definitely not 2100. If we look at 1.7, okay, we can go up, we can add a little more carbon dioxide because we're at a higher temperature, that we would pass that up in 14 years. That would be our 83% chance of staying under 1.7. If we go to the worst one right here, 1450, and kept adding 40 gigatons per year, we'll pass that one up in 36 years. That would be 2057. That's not 2100. That's where we're trying to get to 2100. Now, if we look at our worst outcome, at least the worst one we want to consider, 2.0, we could add 900 more gigatons of carbon dioxide. Unfortunately, we'll do that in only 22 years if we keep going as we're going. 22 years, and that would put us at 2043. We would blow past that one. There goes our 83% chance. If we come over to the worst possibility right here, 2300, that would take 58 years, but that means we would blow past that number in 2079, and we still have 20 more years of time before we get to 2100. So that would mean we probably blow past 2 degrees. So remember that 2 degrees in those red little charts. That didn't look real good. So as we go add more and more carbon dioxide, the odds go down that we could meet these goals over here. Now it's actually a little worse than that because they're not accounting for the methane and the nitrous oxide that we're also putting out. So we have to also cut back on these guys. And if we don't, then you come over here, say we could put in about 220 equivalents of gigatons equivalents of carbon dioxide. So we'd come up here and subtract that. So instead of 300, we'd have 80. 80 we blow past in 2 years, which would wipe out this 83% chance. So this is something we want to also avoid. All right. Now, if we keep going the way we're going, 40 gigatons per year, which actually 2019 was 43, that's more. Multiply by 30, that takes us to 2050. That was a goal of cutting all the carbon dioxide to zero. We would have added 1,200 more to this number we've already added up here, 2,400. If we go all the way for 80 years at 40 gigatons per year to 2,100, we'll add 3,200 gigatons of carbon dioxide. That's more than this number right here. Okay, so we would be in really, really big trouble. So anyway, this is just a little summary of the IPCC6 report. It's mostly data. I added in a little of my own interpretation to that. I'd like to end up with someone who I think is very positive in the climate change outlook. This is a Texas Tech professor, Katherine Heyhoe. She's a climate scientist. She made this quote here, again and again, assessment after assessment. The IPCC has already made it clear. Climate change puts at risk every aspect of human life, as we know it. We are already starting to experience those risks today, but we know what we need to do to avoid the worst future impacts. The difference between a fossil fuel versus clean energy future is nothing less than the future of civilization as we know it. She has a very positive TED Talk. I put the link right here. I suggest you listen to that every time you want to build up some hope. And she's coming out with a book in September, Saving Us, a climate scientist's case for hope and healing in a divided world. So I'd like to thank you for listening to this talk. I hope that the IPCC6 report has a little more reality for you. And with your concern, let's try to beat this problem. Thanks a lot.